Alright, welcome to the second video in the velocity unit. Remember, this video is going to be looking now more at the graphical analysis of velocities. So let's first start off with this simple graph. Notice the graph is position versus time. You'll know that it's position versus time by looking at the axes here. X, which is the universal abbreviation or variable for position, and that's measured in meters, and then time, which is measured in seconds, is on the x-axis. So we know we're looking at a position versus time graph. The question is, what is the object's average velocity for the duration of the 30 seconds? If you recall from the previous video, average velocity, and the key word there is average velocity, is defined as the change in displacement, or change in x, over the change in time. So if we look, the change in position goes from 0 all the way up to 40. And so the delta x would be 40 meters. Now, what time does that take place in? Well, the time, like we said in the problem, is 30 seconds. So the average velocity is 40 divided by 30, or in other words, approximately 1.33 repeating meters per second. Now, that's the average velocity. If you look at the actual movement of this object, it's not constant. For example, the first 10 seconds, the object was moving at approximately 1 meter per second. And I found that out by taking the slope of that line. Rise, which is 10, over run, which is 10, gives you a velocity of 1 meter per second. If we were to look at the slope of the second line, we can look right away and we can tell it's going to be steeper or faster. But let's actually figure out what the slope is for this line. If you look at the rise, or change in x, it's going to be 10, 20, 30 over 10, which is 3 meters per second. And then finally, look at the last 10 seconds. Notice that the object does not change position. It stays at the 40 meter mark for those 10 seconds. So if an object stays at the exact same position for 10 seconds, we must conclude then that the velocity is 0 meters per second. So as you can see, the velocities are actually changing throughout this entire duration. But the average velocity takes into consideration what was the overall delta x over the overall delta t. Now, these individual velocities right here are what is known as the instantaneous velocity. The instantaneous velocity, and we'll talk about this more in Unit 3, is the velocity at the exact moment of specified time. So for example, if I said, what is the instantaneous velocity at time equals 5 seconds, we would find 5 seconds right here, and we would say, what's the slope at 5 seconds? The slope at 5 seconds is 1 meter per second. So while the average velocity is 1.33 meters per second, the instantaneous velocity at the exact time of 5 seconds would be 1. Like I said, that will come more in handy in Unit 3. Let's continue our scalar and vector discussion now with two other terms that you'll want to be aware of. The first term is speed, and the second one is velocity. These two terms, just like distance and displacement, might seem interchangeable to the untrained physics mind. But we're going to know better than that. We're going to know that there actually is a difference, and we want to make sure we use the right term. Speed is the scalar measurement, and speed is simply how fast is something going. So if you remember my example for the scalar, speed would be something like 40 miles per hour. Vector, on the other hand, would obviously be velocity. And velocity is not only how fast something is going, but the direction it is going. So for example, 40 miles per hour going east would be a vector quantity. Now in physics, we aren't going to use the north, south, east, west as much, although it will pop up. Instead, we're going to use the positive and negative more often to indicate direction. All right, so let's go ahead and look at an example now, kind of throwing everything together. Notice that I've put in a position versus time graph, and I've got a line graphed. Right away, I noticed something. I noticed that the movement of this object is linear. And remember, a linear line indicates constant velocity because the change in position is the same per unit of time. So first of all, what do we know about this object? So the first thing I know is that it's moving at a constant velocity. What else do I know about this object? Well, I also noticed that the slope is positive. Do you remember what a positive slope indicates? A positive slope indicates that it's moving away from the origin. And finally, one more important piece of information to note is that this object does not start at the origin. Notice at time equals 0 seconds, the object actually starts up here at the 5-meter mark. So I'm going to say the object also starts at 5 meters. You can see that a lot of information comes from a very simplistic looking graph. Now the second question says, what is the average velocity? Remember, average velocity is delta x over delta t. If we look, delta t, or the time for this, is 5 seconds. So we're going to be looking at 5 seconds of travel. Now, what's the delta x? It might be tempting to want to go ahead and put 25 in here. However, the change in position for this object went from 5 meters to 25 meters. So the change in x, or change in position, was actually 20 meters. And so the average velocity for this object would end up being 4 meters per second. Finally, it says, what is the math expression of this? This is very important. Many times in physics, it's going to ask you for a math expression for some sort of movement or motion of an object. Remember, back up here, I talked about what the shape of this line is. And the shape of this line, the shape of this movement is a line, or linear. So if you think about what is the math expression for a linear fit, it's y equals mx plus b. In physics, however, we don't like to keep things in math terms. We like to give things physical meaning. We want to talk about what's the physical meaning of the slope. So instead of leaving it as y equals mx plus b, we're going to change all these variables to be something that means something to us. When you think about this y equals mx plus b, think about what are variables and what are actual values. The y and the x, these are actual variables that correspond to the y and x coordinate of the axes. The m and the b, on the other hand, are actual numbers. The m is the slope, and the b is the y-intercept. So when I put this in physics or math expression, I want to make sure that I put everything in appropriately. So first let's go through and let's go ahead and look at the y and the x. The y in this case is position. Now you can write position, or remember the actual accepted variable for position is x. That might seem kind of weird considering we have an x right here. But remember, position, the variable for position is x, and that's why it's put in the y spot, because the y-axis is position. Equals, I'm going to leave m out for a second. What is x? Well, the variable for x is time, and the commonly accepted variable for time is t. Next, let's go ahead and look at our slope and our y-intercept. The m is the slope. Remember, what is the slope of a position versus time graph? The slope, which is measured in meters per second, is the velocity, and we already figured that out from the second question. The slope, or velocity in this case, is 4 meters per second. So I'm going to go ahead and put in the slope is 4. But make sure, anytime in physics, when you put a number in, you need to make sure you put the units with it as well, so it has a physical meaning. 4 means nothing, but 4 meters per second means velocity. So the 4 meters per second is the m. And finally, we need to put in there plus whatever the y-intercept is. In this case, the y-intercept is going to be measured in meters. And in this case, the y-intercept was 5. So I'm going to put in 5, but remember, I have to put in a variable, or excuse me, a unit that goes with that in order to give it some physical meaning. In this case, the unit is meters. Now, what is the physical meaning of this y-intercept? The physical meaning of the y-intercept in this graph is the starting point. Remember, it started at 5 meters. So there it is. Our math expression is x equals 4 meters per second times t plus 5 meters. All right, let's look at something different. This question has us wanting to sketch a quantitative x versus t, or position versus time graph, for the following description of motion. An object starts 10 meters away from the origin, walks at a constant 2 meters per second for 2 seconds, stops for 1 second, then walks towards the origin going 1 meters per second for 4 seconds. All right, that might seem like a lot of information, and for the first time it probably is, but let's go ahead and break it down. First of all, it wants us to sketch a quantitative, meaning numbers are going to be important here. Secondly, I notice it's a position versus time graph, and we've seen a lot of those. So let's go ahead and label our axes. The position always goes on the y-axis, and it's measured in meters, and the time always goes on the x-axis, and it's measured in seconds. All right, the next thing I want to notice is I want to figure out what's going to be my intervals. For example, time. What do I want to make time go out to? Let's think about the actual motion of this object. It looks like the motion of this object moves for 2 seconds, stops for 1 second, and then goes back for 4 seconds. Or in other words, is moving for a total of 7 seconds. So I'm going to mark out 1, 2, 3, 4, 5, 6, and then 7 right here. And we can go ahead and label all these since it's not really that difficult. 5, 4, 3, 2, and 1. Remember, when making your graphs, it's important to make sure that all your intervals are even. On the y-axis, that's my position. I want to figure out what's my greatest position and what's my least position to figure out what I should make my scale. It looks like the object starts 10 meters away. Then it walks at a constant 2 meters per second for 2 seconds. If we think about the fact that velocity, or average velocity, is equal to change in x over change in t, and I know my velocity is 2 meters per second, and the time is 2 seconds, I can actually solve for what's the delta x by multiplying those two. 2 times 2 is 4. You might also use common sense and figure out if you're moving at a rate of 2 meters every second, and if you go 2 seconds, it's going to be 4 meters. That's another way to figure it out. So if I started 10 meters away and I walk an additional 4 meters, that means I'm now up to 14 meters. I stop for 1 second, so I don't move any position there, and then I walk back towards the origin. So it looks like my maximum position, or my greatest distance away from the origin, is going to be 14 meters. So maybe I'll make my interval on my y-axis go up by 2 meters for every notch. So 2, 4, 6, 8, 10, 12, and finally 14 here. And it's always a good idea to get in the habit of labeling your axes so you don't get confused. All right, now that we have everything labeled, let's go ahead and plot our data points. An object starts at 10 meters. So at time equals 0 seconds, the object is already at the 10 meter mark away from the origin. Then it says the object walks at a constant 2 meters per second for 2 seconds. Couple different ways you can look at this. The first way is the way we've already gone over, and that is in 2 seconds, the object is now 4 meters away from the starting point. And if the object started at 10 meters, at 2 seconds, it's now at the 14 meter mark. Another way you could have looked at this is said, all right, if an object is moving at 2 meters per second, that's a velocity. And remember, velocity is the same as slope. So I could have made a slope of 2. Either way, you should get a line that looks like this. All right. Then we're told the next leg of the motion, for 1 second, the object is stopped. If an object is stopped, that means it has a 0 meter per second slope, or a velocity, and therefore a slope of 0. So I'm going to draw a line for the next 1 second that's going to be a horizontal line that has no slope. Finally, I'm told that the last part of the motion for 4 seconds, the object is moving at 1 meter per second. Once again, you can look at this a couple of different ways. The first way is figuring out, okay, if the object has a velocity of 1 meter per second and the time is 4 seconds, what is the change in position? The change in position would be 4 meters. But notice, the object is walking towards the origin. So what does that mean? If the object is walking towards the origin, that means the slope is actually negative, and therefore the change in position is negative. So it looks like the object goes back 4 meters, back to the 10 meter mark. But this is in 4 seconds. So at the end of the next 4 seconds, 1, 2, 3, 4, the object will be back here at 4 meters. Or 10 meters, excuse me. If I connect that with a line, I end up getting a slope that looks like that. And if you were to do the math, you would notice that line actually has a slope of negative 1 meter per second, while this slope over here had a 2 meter per second. You can also see qualitatively that the object is faster here than here, simply because the slopes are different. So we have successfully created a quantitative position versus time graph. Now you'll notice there is a second graph off to the right, and I drew that for a reason, because now I'm going to introduce a second type of graph, and that is the velocity versus time graph. So I'm going to erase that line real quick. And what we're going to do now is we're going to actually create a velocity versus time graph. Now time is still in seconds, but velocity, what do we measure velocity in? It's not just meters, but it's meters per second. Alright, you'll notice that the velocity graph actually has a positive and a negative quadrant. Right here, where it's 0, is the origin for the velocity graph. Now, think about it. In this graph right here, we're not graphing position anymore. We are graphing velocity. In a lot of cases, this can be an easier graph to make than a position versus time graph. For example, let's look at the first 2 seconds. For the first 2 seconds, and let me mark this out, 1, 2, 3, 4, 5, 6, and 7 seconds. You always want to mark it the exact same way you did the position graph, for the time anyways. That way you can compare apples to apples. Alright, for the first 2 seconds, we are told the object is going to a constant 2 meters per second, meaning the velocity is not changing. The object is not speeding up or slowing down. Alright, so if the object is going 2 meters per second, I'm going to want to draw a line that represents 2 meters per second. So let's make every 2 squares 1 meter per second, there's 2 meters per second, and then 3 meters per second. Okay, if for the first 2 seconds the object is moving at a constant 2 meters per second, I'm going to draw a line there. Notice it's a flat line, but in a velocity versus time graph, a flat line does not mean the object is not moving, but simply means that the object is going at a constant 2 meters per second. A flat line on a position versus time graph indicates that the object is at rest, because notice it's because the position is not changing. But in this graph, the velocity is not changing, and that's why it's a flat line. Next, we're told the object stops for 1 second. Well, that means for the next 1 second, the object is going at a constant 0 meters per second. So I'm going to put a flat line right here. Finally, we are told that the object then walks towards the origin going 1 meters per second. And we know in reality that's a negative 1 meter per second because the object is going towards. So, because we know that, and we know that the velocity is negative 1 meter per second, I'm going to go ahead and draw my intervals down here, negative 1, negative 2, negative 3. Remember, you got to keep everything evenly spaced. And so I'm going to actually draw a line at negative 1 meter per second for that last 4 seconds. Now, to finish things up, we don't want to leave the graph just by these horizontal lines, but instead we want to show that it's continuous. So I'm going to go ahead and connect these lines with some sort of connection or slope. Now, in all reality, there's no way an object would change velocity that fast. But for all intents and purposes, we can say this is essentially a vertical line here and here. Now, there's some very key information that can be drawn from this graph, and that's this. Notice we made some connections with a position versus time graph. We said that the slope of a position versus time graph would tell us velocity. For example, the slope right here is 2 meters per second, and that gives us the velocity right here. The slope here is 0, and that gave us the slope right here. And finally, the slope here was -1, and that's the portion of the graph here with -1. If you wanted to go the other way and figure out information about a position versus time graph from a velocity versus time graph, there is a way to do that that's called area. So let's actually do that. For example, right here you can look that there is kind of a rectangular shape here and then a rectangular shape here. Notice there's no shape here because it lies right on the 0 axis. Okay, what would be the area of this rectangle right here? Remember, the area of a rectangle is length times width, or base times height, however you want to think about it. So in this rectangle, the base is 2 seconds, and the height is 2 meters per second. If I multiply those out, 2 times 2 is 4, and the seconds cancel out, leaving me in meters. So what does the area underneath this graph tell you? That tells me in 2 seconds the object moved 4 meters. And guess what? We actually figured that out over here. Same thing. Let's find the area under this graph. The base is 1, 2, 3, 4 seconds. And be careful, the height in this one actually is -1 because it goes down. Units there is -1 meters per second. 4 times -1 is -4. Seconds cancels out, and I'm left in meters again. That tells me in the last 4 seconds the object went back, or a -4 meters. So if I look total, the object went forward 4 meters and backwards 4 meters. So what would be the total displacement of this object? The answer is 0. And we actually figured that out. The object started at 10 and ended up at 10. That's some amazing connections. So we figured out a lot of information from this one slide. We figured out how to make a velocity versus time graph. We figured out how to make a quantitative position versus time graph. And we also figured out that to go from a position graph to a velocity graph, that we use the slope. And to go from a velocity graph to a position graph, we use the area. If you are in calculus, or if you've ever taken calculus, this is the exact same thing as derivatives and integrals. The slope would be the derivative, and the area would be the integral. However, if you're not in calculus, don't worry about making that connection. All right, let's look at some more examples. I'll go through one more, and then I'm going to give you a few examples to do on your own. All right. In this example, the position versus time graph is already given to us. It wants us to create the velocity versus time graph. Okay, easy enough. Remember, to go from a position versus time graph to a velocity versus time graph, we're going to be looking at slopes, because slopes tell us velocities. So let's look at this first part right here. From the origin to right here, the velocity is constant because it's linear. Okay, so let's figure out what that slope would be. The change in position goes from 0 to 5 meters in 5 seconds. So 5 meters divided by 5 seconds gives us a velocity of 1 meter per second. So that means for the first 5 seconds, the object is going at a constant 1 meter per second. So I'm going to show that by going over here, and at the positive 1 meter per second, I'm going to draw a horizontal line to 5 seconds. Once again, a horizontal flat line in a velocity versus time graph does not mean the object is not moving. It means it's going at a constant velocity. Okay, The second one is a little faster because the slope is steeper. In this case, the change in position is still 5 meters because it goes from 5 all the way up here to 10, but the timing is different. It's faster. It goes 5 meters in 2 seconds. And that's 1, 2. So 5 meters divided by 2 seconds gives us a velocity of 2.5 meters per second. So if I go over to my velocity versus time graph, I'm now going to draw a horizontal line at the 2.5 meter per second for the next 2 seconds. Next, it looks like the object does not move for 1 second. It stays at the 10 meter mark, meaning the slope is 0. And if the slope is 0, that means the velocity is 0. So for 1 additional second, so from time 7 to time 8, I'm going to draw a line right here on the 0 meter mark to indicate a 0 velocity. Finally, let's look at the last part of motion. Notice that it's negative, so I know I'm going to be down here somewhere. I notice that the object goes from 10 meters down to 7. So it looks like the change in position is negative 3 meters. And the amount of time that happens is in 2 seconds. So the velocity is negative 1.5 meters per second. And so I'm going to draw a line for the last 2 seconds down here at the negative 1.5 meter per second mark. Finally, remember, we want to connect these with vertical lines. Once again, it's not perfectly realistic for an object to change velocity that fast, but for all intents and purposes, it's fine. Now let's figure out what the displacement was. Remember, you can find the displacement by finding the area underneath the velocity versus time graph. Okay, so let's go ahead and look at that. We got 2 shapes here. The first shape is right here. It's this odd kind of L-shaped figure right here because this whole area is above the x-axis. Right here lies perfectly along the x-axis, so there's no shape here, but then we get a rectangle right here. Okay, let's first figure out the area of this above the x-axis shape. Kind of looks a little weird, but we can actually break this up into 2 oops, that was bad. We can break this up into 2 separate rectangles. There we go. Okay, so I'm going to do my best here to draw a line. There we go. Okay, so let's actually figure out the area for these 2 rectangles, and then we'll just add them together. This first rectangle is 5 seconds times 1 second. So 5 seconds times 5 seconds times 1 meter per second. So let me write this out. 5 seconds is the base, and the height is 1 meter per second. The seconds cancels out, so you'll be left in meters. So the area of this rectangle is 5 meters. Now, over here, the base is 2 seconds. Be careful, it's not 7 seconds, it's 2 because you only move over 2. Times the height. The height is 2.5, and the units are meters per second again. Seconds cancels out, and so 2.5 times 2 also ends up being 5 meters. So the total displacement for the first 7 seconds is 10 meters. Let's just compare and see if that actually makes sense. For the first 7 seconds on this graph, where did we end up going? We ended up going from 0 all the way up to 10. So that makes sense. Now let's figure out what's the area for this rectangle. The base is 2 seconds because we're going from time 8 seconds to time 10 seconds. So change in t or base is 2 seconds. But the height is negative 1.5 meter per second. Seconds cancels out, and negative 1.5 times 2 is negative 3 meters. So the displacement here is negative 3 meters. So if it's 10 meters for the first 7 seconds, and negative 3 meters for the last 3 seconds, since there was no change in position here, that means the total displacement overall for the whole 10 seconds should be 7 meters. And let's see, is that where we ended up? Yes, it was. So we were able to figure out the change in displacement from the velocity versus time graph. All right, at this point, what I'd like you to do is I'd like you to pause the video, and while it's paused, I want you to describe the motion of the following object. Be as specific as you possibly can. Okay, hopefully you got this information. The object starts at 20 meter mark, at the 20 meter mark. For the first 1 second, it goes 0 meters per second, or is standing still. For the next 2 seconds, it goes 20 meters per second. Then is at rest for 0 meters per second. And then finally moves back, and this should be negative, excuse me, moves back at negative 26.67 meters per second. The tricky thing there that you may not have caught is that the object starts moving at time approximately 4.5 seconds and then ends at 6 seconds. So the delta t there is 1.5 seconds. That might have been a little tricky. Now what we're going to do is we're going to go ahead and give you an opportunity to transfer this data over into a velocity versus time graph. Pause the video, then hit play to reveal the answer. Okay, let's go ahead and check to see if you got the same thing. For the first 1 second, remember the object was moving at 0 meters per second. Then the object moved for 2 seconds, going 20 meters per second. Then stopped for about 1.5 seconds, going 0 meters per second. And then finished off for the last 2.5 seconds, going to approximately 26.67 meters per second. Notice my scale, time went to 7 seconds, and then my velocity over here, and I should label this, excuse me, velocity in meters per second, and then time is in seconds. The velocity I went up by 5s, 5, 10, 15, 20, 25, 30, and then same below. Alright, you should be getting pretty familiar with this. Sketch a velocity versus time graph from the following, and then answer the questions. We're not going to sketch the graph since we've done practice with that, but let's go ahead and answer these questions. The first question says, what is the average speed over the 100 seconds? Now, we haven't really talked about the concept of average speed. We've talked about the concept of average velocity. So average velocity, if you remember, was change in position over change in time. Speed, however, is going to integrate scalar quantities. So time is going to still be the same, but instead of doing change in position, I'm going to simply just talk about change in distance, or just simply distance. So if I look at the distance covered by this object, the object went up 400 meters, stayed still, and then went back down 400 meters. So the object moved 800 meters in a span of 100 seconds. So the average speed would be 8 meters per second. Now, the average velocity means change in position over change in time. Well, if you look, the time is still 100 seconds, but what was the change in position? Well, the object started at 0, went up, over, but ended actually up back at 0. So the displacement, or change in position, was 0 meters. And so the average velocity is 0 meters per second. That's really difficult to understand for someone because they're looking at this graph and saying, well, the object was moving. How can an object be moving, have a 0 meter per second average velocity? You have to remember that average velocity is vector, meaning it's incorporating direction. It looks like the first half of motion was positive, and then the second half of motion was negative. It makes sense that when you average these two things out, but positive and negative, you're going to get something that is 0. Alright, we're almost done. Let's go ahead and look at 2 more examples. This one actually looks a little different. It says, describe the motion of the object and be as specific as possible. The key thing to notice here, and don't get confused, this is a velocity versus time graph, not position. So we have to be careful. For the first 2 seconds, it looks like the object is going 0 meters per second, so it's not moving. Then the object, for the next about 3 seconds, is going 0.5 meters per second, pauses, and then goes negative 0.5 meters per second. Now, we can also use the little trick we know about area. For this rectangle right here, the area would be base, which is 3 seconds, times height, which is 0.5 meter per second. The seconds cancel out, and 3 times 0.5 gives you 1.5 meters. We can do the same thing for this rectangle down here below the x-axis. The base is still 3 seconds. The height is 0.5, but it's negative. When the seconds cancels out and we multiply those together, we end up getting a negative 1.5 meters. So if we know the object displaced 1.5 meters here and then displaced negative 1.5 meters here, we can conclude that the object had a total displacement of 0 meters for this full 10 seconds. Notice there is no way to tell from a velocity versus time graph where the object actually started. All we can do is figure out what the displacement was. We have no idea where this object started. It could have started at the origin, but it could have started at 10 meters away from the origin. All we know is that the object is going to end up in the exact same place that it started. Finally, let's look at one last practice. In this picture, you have a position versus time graph and 4 objects labeled A, B, C, and D with their respective slopes. The question is, rank the following below from the lowest speed to the highest speed. Then do the same for the velocities. Remember, speed is scalar, so we're only going to look at magnitude. So I'm going to go ahead and set up my greater than signs. And we're going to put in the letters going from lowest to highest. So what would be the lowest speed, or the object that is moving the slowest? Remember, we're just looking at magnitude, so ignore for a second any negative or positive slopes. It only depends on the actual steepness of the slope. Well, C has a horizontal slope, or a zero slope, meaning it's not moving. So C would have the lowest speed. The next highest slope looks like it's going to be D. Then B, and then finally A. Notice once again we're just going off of steepness of slope. Speed has nothing to do with positive or negative. Now let's do the exact same thing, but now we're going to look at velocity. Now sign does make a difference. So if we're thinking about that, I know C is horizontal, so it's neither negative or positive. B and D are positive slopes, but A is a negative slope. So right away, I know A has the lowest velocity simply because of its negative slope. Then C would be the next lowest because it's 0. D then would be the next, and finally B would have the greatest velocity because it has the steepest slope in the positive region. This concludes the video on the graphical analysis for velocity and position. The final video will be video 3, which will deal with motion maps.